Hi, thanks for joining me. Today I've got an interesting problem involving limits. We want to compute the limit as n goes to infinity of the fractional part of 3 plus 2 root 2 raised to the n. And so these curly brackets here mean fractional part, so that's simply the bit after the decimal point. So for example, the fractional part of 2.6 is just 0.6, so the bit after the decimal point. The fractional part of pi is just 0.14159, and so on. And then the fractional part of an integer, so the fractional part of 7, say, is just 0, because there's nothing after the decimal point. Anyway, if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to jump straight into a solution. Okay, so before I get stuck into a solution, I just want to make a quick remark about this guy here. It's not particularly clear why a limit should even exist, because we're taking some number, raising it to the power of n, and then just looking at the bit after the decimal point. It's not clear why that should converge to a number, let alone us being able to find that particular limit. But we can actually do that using a really nice trick. What we're going to do is consider 3 plus 2 root 2 to the n, what we have here, but now what I'm going to do is add on its partner, 3 minus 2 root 2 to the n. And now the motivation for this here is because this problem is also to do with the bit before the decimal point and the bit after the decimal point. The bit after the decimal point is what we're interested in, but it would be good if we have a good idea about what's before the decimal point. And that is, the integer part of this number here. Because if we can write 3 plus 2 root 2n as some integer plus or minus a very small real number, where that small real number is less than 1, then we'll kind of have an idea of how to solve this guy here. And the way we're going to do that is by considering this number here, and you may have seen things like this before, but I claim that this here is an integer, regardless of what n is, and that kind of is bizarre at first glance because we've got, root 2's here, root 2's here, so when we add them up, we expect to see a bunch of root 2's, but because of this minus sign here and this being a plus sign, it actually cancels, and we can prove it quite easily just using the binomial expansion formula. So if I use binomial expansion on this guy here, this is equal to the sum from j equals 0 to n of n choose j times 3 to the n minus j times 2 root 2 to the j, like so. And then on this guy here, this is equal to the sum j equals 0 to n choose j, 3 to the n minus j times now minus 2 root 2 to the j. But of course I can just bring this minus out and write it as minus 1 to the j, like so. So you've got this guy here, obviously that's not supposed to be equals, that's supposed to be plus. This guy here plus this guy here, and we can see most of the terms are the same, n choose j, 3 to the n minus j, 3 to the n minus j, 2 root 2 to the j, and 2 root 2 to the j there, but this time we've got a minus 1 to the j here. Obviously minus 1 to the j is 1 if j is even, and minus 1 to the j is minus 1 if j is odd. Now if j is odd, then this root 2 here will be to some odd power, so it will still have a root 2 in it, which is kind of ugly. But thankfully, because when j is odd, this guy here is negative, it's going to cancel with the corresponding 2 root 2 j to the j here. So this will cancel with this. So the only thing we need to do is consider when j is even, but that's perfectly fine, because when j is even, this guy here, the root 2 is going to sort of square out to be an integer, and similarly this is going to square out to be an integer. So we've just got an integer plus an integer, and obviously that's an integer. So go through the details yourself if that hasn't convinced you, but hopefully you can see that this expression here will always be an integer, and hence this guy here is always an integer. Now perhaps you can guess what my next step is going to be, but let me clear up the whiteboard and I'll continue. Okay, so we've just shown that this expression here, 3 plus 2 root 2 to the n plus 3 minus 2 root 2 to the n, is always an integer, so I can write this equals, say, tn sub n. So t sub n, where tn is an integer. But now what I'm going to do is just write it as tn minus 1 plus 1, like so. And it might be a bit weird to see why I've done that, but it'll become clear in just a second. Now what I'm going to do is just subtract this 3 minus 2 root 2n from both sides. So I get that 3 plus 2 root 2 to the n is equal to tn minus 1, which I'm going to put in brackets, plus 1 minus 3 minus 2 root 2 to the n, like so. Now tn is an integer, so tn minus 1 is an integer. So we're not really worrying about this guy because we only want to consider the fractional part of this guy. We're only really interested in this thing here, 1 minus 3 minus 2 root 2 to the n. Now, 2 root 2 is bigger than 2. So 3, and it's also less than 3 because root 2 is 1.4 something. So this guy here is going to be a positive number between 0 and 1. So that means when you raise it to the n, it's always going to be a number between 0 and 1. And then when we do 1 minus it, this guy here is going to be between 0 and 1. Like so. So in fact, regardless of what this Tn is, we can see that the fractional part of this guy here, we're going to get rid of this, and we're just going to be considering this thing here, because this is the integer part and this is the bit after the decimal point, because it's a number between 0 and 1. So we have that the fractional part of 3 plus 2 root 2 to the n is equal to this guy here. And now the last thing we want to do is just take the limit as n goes to infinity on both sides. So if we do that, like so, we just have to compute the limit as n goes to infinity of this guy here. But remember, this thing here is a number between 0 and 1. So when we take that to the power of n, that's going to tend towards 0. So this thing's going to vanish, and we're just left with 1. So in other words, the limit as n goes to infinity of the fractional part of 3 plus 2 root 2 to the n is equal to 1. And that is our solution. I hope you have enjoyed this cool proof. When I first saw this limit problem, I thought this is a bizarre problem. No way does this have a limit. I don't really want to solve this because I think this is a troll, but it turns out there is indeed a limit, and it's not too difficult to compute. You just need to use that very nice trick about adding its sort of radical complement or radical conjugate, whatever it's called. And yeah, and then it kind of pops out very nicely. Anyway, I hope you have enjoyed this video. Thanks for watching. I'll catch you in the next one. Have a great day.